Hi everyone, in this section we are going to learn about backtracking, which is a very powerful concept in algorithmic problem solving. So it's an algorithmic technique in which we recursively try to build solutions. We try to search through the entire search space to solve a computation problem. So you might ask, okay, give me one example. So basically, we would be discussing various problems such as popular problems are n-queen problem, finding permutations, finding subsets. So each of these problems can be divided into one of these categories. One is a decision problem, one is a optimization problem, and one is a enumeration problem. So what is a decision problem? In a decision problem, we check for a feasible solution. For example, let's say you are given a grid, and in that particular grid, let's say there are certain cells that are blocked. Maybe this cell is blocked, this is blocked, this is blocked, and this is blocked, and you're standing here and you want to tell me whether it is feasible to start from this cell and reach this particular cell. Okay, so this is like a checking for a feasible solution. So you have to tell yes or no whether a solution is possible or not. Now the solution will depend upon certain constraints that are given in the problem. Okay, so the constraints can be on the movement, how the person can move, whether he can move left or down. If it can move only left and down, right and down, then there is no way we can reach this particular cell. But if the diagonal movement is also allowed, yes, in that way we can reach this particular cell. So this is a decision problem. Okay, another could be an optimization problem, maybe where we want to find out the best solution. Okay, so maybe we are given maybe a set of nodes, and let's say we have something, let's say from every node we can go to every other node. Okay, maybe we want to find out a path which covers all the nodes. Okay, maybe find a path which covers all the nodes, but you in a minimum cost. Okay, in a minimum cost, let's say. So this is like an optimization problem. So maybe a path which covers all the nodes but in a minimum cost, let's say a, b, c, d, e, and f. So from every node to every other node there is some cost associated. So this is like a finding out the best solution out of multiple solutions that we can do. So this is again a kind of a backtracking problem. An example could be something similar to traveling salesman problem, if you have heard. Okay, so another is a enumeration problem where we need to find out all the possible solutions. So basically, let's say we are given let's say a string abc, and we want to find out all the subsets of this particular string, or maybe we want to find out all the permutations of this particular string. Okay, so if we talk about permutations, it would be abc, cba, bac, bca, and so on. So we will have 3 factorial, that is 6 permutations. So this is about finding all the permutations. Okay, so we will discuss these type of problems in this particular section, and we'll also discuss some popular classical problems which fall into one of these categories. So classical problems like a rat in a maze problem, where a rat is stuck in a maze. There is a problem which is known as n-queen problem. We will discuss that. We'll discuss phone keypad problem. We'll discuss Sudoku solver. Okay, so these are some common problems that you will find. There is knight's tour problem. Okay, so these are some common problems that you will often see in backtracking. There is not a lot of variety. If you understand and learn how to solve these basic problems, you can easily apply those concepts to new or unseen problems in backtracking if you encounter. Okay, so that's the end goal of this particular section, and I hope you would really learn a lot. Hi everyone, so now we are going to discuss the first problem, in which we need to find the subsets of a given string. Okay, so sample input is abc, and you can see these are the possible subsets that we can have. So what is a subset? So subset is a small part of the string which may or may not contain continuous letters. Okay, so if we have, let's say, 3 letters, then for every letter we have 2 options. Either it will be a part of the subset or it will be not. It will be part of the subset or not part of the subset or not. Okay, so that means we have 2 into 2 into 2, that is 8 number of options to create subsets. And you can see, if we exclude all, then it is a null subset. If we include all, then it is ABC. If we include BC, then it is BC. If we include AB, then it is AB. If we have this one, ignore this one, or take this one, then it is AC. Similarly, we have AB, ABC, AB. So these are the 8 possible options that we can have. Now we need an algorithm that computes this and prints all the subsets. So let's see how we can do it. So first of all, we are having an input array. Okay, so the idea here is, if you try to break this problem recursively, what you can do in order to find subsets of ABC, I can say I will make this as a sub problem, finding subsets of the remaining string as a sub problem. Let's say this string starts from I, then from I plus 1 till the last is a sub problem that will be solved by recursion, and I'm only worried about what I can do at this particular point. So with A, I can actually make 2 copies, a subset in which A is present, a subset in which A is not present, and I can say, okay, go and find the subsets of BC. Okay, so null with subsets of BC. And how do you find subsets of BC? Let us say recursively we have the subsets of BC, so it would be B, or it would be C, or it would be BC, or it would be null. So if you append A with them, it would give you AB, it would give you AC, it would give you ABC, and it would give you A. And here also, if you find subsets of BC, it's BC, BC, and null. Okay, I'm not written in a particular order, but if you add a null with all of them, that means you have not taken A. Okay, so here we say, okay, take A along with subsets of BC, and here we say don't take A. Okay, don't take A with subsets of BC. So it becomes nothing but BC, BC, and null. Okay, so if you talk about these 4 and these 4, these are the 8 subsets that we were talking about. Okay, so BC will give you 2 into 2, that is 4 subsets, and with these 4 you actually make 2 copies, one with A and one without A. Okay, one with A and one without A. So this gives us a hint of how to compute or how to solve this problem. So effectively, let's again try to draw the recursion tree and see how this problem will actually get solved. So let's say we have this input array that is initially A, B, C, and a null here. Let's have another output array that is initially empty. Let me call it as input. Let me call it as output. Okay, so this is also empty. Okay, so now I put a pointer variable I equal to 0 here, and I put a j equal to 0 here. Okay, so in the beginning I'm going to make 2 calls. Okay, I am going to pass this array in 2 calls. Okay, that means if I'm using an array, it will be shared across all the function calls, and we will need to do some work as well. So when is okay, let's make a function call and we will take A. So we will get A here, and this input pointer I will move to BC. Okay, so we are standing at B. So again, in this call, what we are going to do, and in this call that will happen a little later on, what we are going to do, we are not going to take A. So if you take A, then J will move to this index, and if you don't take A, J will still remain here. Okay, J will still remain here. So now what is going to happen, as we discussed, when you're going to come back from this call to this call will actually have a here, and when you're going to make this call will also have a here. Okay, but that A is not going to matter a lot because we are going to overwrite it. Okay, I just make a dotted A here. We don't want to take this A, but it would be present because of the backtracking. The array is same across all the function calls. So now let us first focus on this call. So at this point, I is moved to one place ahead. I will go here, and J has also jumped one index ahead, because by reading one input letter, you have copied one letter in the output array. Okay. So now in this function call, what you're going to do, you're going to say, okay, I will take B and I will not take B, you will again make two function calls. If you take B, then B will come here, and if you don't take B, then this array would look something like this. Okay, and if you take B, the J will move one step ahead. Okay, then in the next function call, I would jump to one more step ahead. Okay, and similarly here also we will be doing the same calls. If you take B, it would look something like this. If you don't take B, it would look something like this. Okay, and now in the final step we have I which is equal to C. Some of you may ask, why are we drawing these calls in parallel? These calls will not be in parallel, they would be in the left to right order, but just that we will forget the state when we will come back to this particular point. I'm just drawing in parallel. Okay, so J will be here and J would be here. Okay, and if you take C here, it would be something like this: A, B, C, and J would jump here. If you don't take C, it would be like this: A, B, and you can see J would be here. If you take C, it would be like AC. If you don't take C, it would be like A only. If you take C, it would be BC, and if you don't take C, it would be like B. If you take C, it would be like C. If you don't take C, it would be like null. Okay, so this is going to be null array. So I've drawn it here. Okay, so now we are going to jump to the final call. In the final step, this I would be at this index I, that is null. So if it is null, we will put the null at the jth index and we will print this output. So we put a null here and we are going to print this. We put a null here and we are going to print this. But this is actually the recursion tree for this particular problem. Okay, but some of you may ask how these calls are being made in parallel. Okay, so what will happen is, firstly, now I will show you the exact flow how recursion actually will work. So firstly, this call will happen from here, this call will happen from here, this call will happen. So when you're in this particular call, rest everything is not happened yet. Okay, remember, rest everything is yet to happen. So from this step, this is how it is happening. Okay, so at this particular point, you have your J which is here, and you have accepted all the letters from the input, like we filled the array. So it is ABC null, but from this point we have done the printing. We will get our first output, that is ABC, and the base case will say return. So when we say return, we will go back one step back, we'll go one step back. Okay, so I've actually there would have been one more step like this one, ABC and null. So null was not here, and from here we go one step back, in which J is going to come here and J was actually here. So this is actually the base case. Okay, this is actually the base case. So I had less space to draw, so I drawed the base case in the same output, but there would be another call for the base case. So in the base case, we are putting a null, we are printing the output, and we are going back. So when you're going back, this array and this array are actually same, so you will actually have a null here. Okay, but J will be at this place. So from here you will say, okay, my work is done, I have printed whatever is to be done for the remaining output, and we will again go back. Okay, so when you're coming back in this particular array, what you will see, you will have actually a C here and you will actually have a null here. Okay, but J would be at this particular index, and when you're going to make this call, you are going to say, let us put output of J equal to null. Okay, so basically this value was already null, and you are overwriting this particular C with null, and then you're making a call in the base case in which you are doing, okay, A, B, null, and you're making this at this particular index, which is again null, and you're printing this output which evaluates to AB. So again, when you're going to come back from here, this is actually going to be AB null null. That is what is going to you're going to see here, AB null null. But again, when you're going to make a call here, the value of J is not going to change. The value of J would be, so when you include something in your input, you say j goes to j plus 1. But when you don't include something in your output, sorry, when you include something in your output, j goes to j plus 1, and if you don't include, j remains at the same index j. So now this array will be actually ab here, ab null null, okay, and you're going to overwrite the jth index with some extra information. Now your input I in this call is at actually c. So what you're going to do, you're going to overwrite the jth index with c. So this b will get overwritten with the value of c, and you will end up getting like ac here, okay. This is what is going to happen. Then again, when you're going to back, this array would be actually ac. Then you again come here, you will overwrite c with a null. Then you again come back, it would be something like a null null, and you again go back, it would be like a null null, and then you go here, but j is not changed, j is at this particular index. Then you get a here, and you're going to override this a with the value of b, because in this function call the I is at particular index b. So this is actually how it's little complex, okay, but just for the sake of simplicity, I first draw the recursion tree. Now I'm telling you what is happening at the leaf node when you're going back, and how we are overwriting the existing values in the array. And this will not need a backtracking step, but what we are actually doing is we are overwriting the previous output with a new output, okay. So what you could have also done is you could have overwritten the previous output with a null and then written a new output, but overwriting a previous output with a new output is also fine, okay. So we are overwriting previous output with new output, okay. But this is actually a backtracking problem. Why? Because when we are going back, we need to do some changes in the array, and we are exploring the entire search space. We are trying to find all possible solutions using backtracking, okay. We are finding all possible solutions, okay, and these are the all possible solutions that we are looking at. So I hope you understood the concept, and in the next lecture I will show you how you can write the code for this problem using a character array, okay. So let's see in the next lecture. Hi everyone. So now let us look at the implementation of finding subsets using recursion. So first of all, we are going to take input some string, and then for that string, what we are going to do, we are going to call this method find subsets that will have a single output array that is shared across all the function calls, and we will try to fill that array, and we'll try to print the output every time we hit a base case, okay. So what we are going to do, we are going to say we are going to have a base case, and we are going to have a recursive case. In the base case, what you can think of is, if input of I is null, that means you have reached till the end of the string. Let's say you are a, b, c and null. Let's say this is your input. So if your input of I is actually null, then that means your work is done, and in the output you have already filled some value, and your j is already pointing to the right place where you're going to fill the value, and you're going to fill this and you're going to print this, okay. So this is what we are going to do in the output, and this is what we have in the input. So for a null input, we don't need to make any further recursive calls. So if input of I is equal to null, then we can say cout output, but before printing output, you should also set output of j equal to null in order to avoid garbage getting printed, and we can say return. That's it. Otherwise, in the recursive case, what we can do, we can say, let us do two things. Let us include the ith letter, or let us exclude the ith letter from the input. These are the two options, okay. So if you want to include a, then how you will do it, you will say, okay, output of j should be equal to input of I. That's it. And you make a recursive call on the remaining string. So if you include a, this is the remaining string, and I would go to I plus 1 and j would go to j plus 1. So you can say find subsets input, output, I plus 1 and j plus 1. If you want to exclude the ith letter, okay, then what you should do, you should say that, okay, I don't care about what is present at the ith index. I will simply find subsets starting from the index I plus 1, and I will not update j. So this call will actually overwrite what was written at the jth index in this particular line number 15. Okay, so this is actually going to do the overwriting. Okay, if you're not sure, if you want to see how we can do it, you can also write output of j equal to null. So instead of a getting overwritten or b getting overwritten, you first overwrite a with null, then null with c, or you could do a with c. That's not going to matter a lot. Okay, this step is optional, but I'm just telling you that since we have now moved j, so whatever was the output in the previous state of the array, that will be getting overwritten, because in the next call you would be overwriting at the jth location. Okay, because we are not changing j. So I think that's the complete code. Now we can test our code and we can call the method find subsets. Okay, and we can give input, output. So in the beginning I is 0 and j is also 0. Okay, so let us try to run our code. Let us try to run our code here, and let me show you the input and output. So if I give abc, then you will see the output is abc, ab, ac, a, bc, b and c, and finally there is a null output as well, which is not visible. So maybe we can check if output of 0 is just null, then we can see out null, just to make sure that this null is visible like this. Okay, this is output. So we are getting a null at the last index, you can see. So now let me draw the recursion tree once again to explain how this code is going to work. So in the beginning we have an output array which is null, we have input string which is abc. So I is here, j is here. We say, okay, let us make two calls. In the first call we say output of j equal to input of I, so it copies a here, and the next call will happen later on, but we are not copying anything, but this a will be a part of this a will go here, but j would be here. Okay, so just assuming that this is not there. Okay, so j would be here, and in this case j would be here. Okay, and again you make two calls. You say, okay, either include b or don't include b. So if you include b, it would be ab. If you don't include b, it would be a. If you include b, it would be b. If you don't include b, it would be null. If you include c, it would be abc. If you don't include, it would be ab. Okay, similarly ac and a, similarly bc and b, and c and null. Okay, finally we say, okay, input of I is going to be null, so you are going to make another call. You say, okay, let me put abc null and print it. Let me put ab null and print it. Let me put ac null and print it. A null, print it. bc null, b null, c null, and finally this is nothing but null. Okay, so if you look carefully, the output order is exactly same as this one: abc, ab, ac, a, bc, bc and null. And that means this is how quickly you can actually draw a recursion tree and verify. So when we are drawing quickly, we are assuming that these calls are happening in parallel, but actually they are not. We are going in a left to right order. So first we are going like this, and then like this, 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 and finally we'll terminate at this particular point. Okay, so if you finally print the output array in the main, what you will get, you are actually going to get the output for this array, so which is actually null, 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 null. So the entire output array would be actually null in the main. So you can verify by printing an output here. Now that's all for this lecture, and in the next lecture I will show you how you can actually print this output maybe in a sorted order, and that we will see in the next video. Hey everyone, so let us move on to the next question, that is finding permutations of a string. Okay, so I know you must have studied about permutations, but let us discuss how we can write a code that can generate all permutations of a array or of a string. So let's see this input. So we are given this input and we know that this string has 3 letters, so we can form 3 factorial, that is 6 permutations. Okay, and we need to print all the 6 permutations that we can think of. So let's see how we can solve this problem. So let us say we have this input string ABC, and the way to break down this problem is how we can generate permutations. Okay, so the most fundamental way of finding the permutation says that, okay, we know we have A at the first place. If I can find out permutations by putting B at the first place. Okay, so what I can say, okay, let us have A at the first place and let us try to find permutations of the smaller string, that is BC. That could be one path. Another path could be, we can say, okay, no, let us put B at the first place and let us try to find permutations of the smaller string, that is AC. So we swap B with A. Or we can do, okay, maybe let us swap C with A. C comes to the first place and let us try to find permutations of the smaller string, that is BA. Okay, and if you do the same thing for the smaller string BC, you can get ABC or you can get ACB. You do the same thing for this, you get either you have A at the first place, you get BSC, or you have C at the first place, you get BCA. Similarly here, either you have B at the first place, you get CBA, or you have A at the first place, that is CAB. Okay, so you can see you got 6 such permutations. Okay, so I hope you're getting little bit idea. So what I'm trying to say is, if you have a string like this, if you have a letter, some letter L here, and you have some letters here, you try to exchange this letter with every possible letter in this particular string and solve the subproblem. How do you solve the subproblem? By making a recursive call. Okay, so maybe if I have A, B, C, D, E here, you swap L with A, L with B, L with C, L with D, L with E, L with F, and you get something like this: A followed by L, B, C, D, E, F. You make a permutation call here. Similarly, you get a B here, you permute this, you get a C here, you permute this, and so on. Okay, and this will again follow the same recursive structure that we are going to see. Now let us try to dive in a little more detail and try to understand the importance of backtracking and how recursion is going to work in this particular case, and then we will jump into the coding part. Okay, so if I say I have ABC here, okay, first I will place A, I will replace A with A. Okay, I'm going to put A, or I'm not going to make any change. I'm just going to make a recursive call on the smaller part. So I come into this branch, I say, okay, I have BC here, and I again start doing work at B. I say, okay, I will put B at the same place, and in the next call I will replace B with C. So I get A, B, C, and I come to this. So now I have only one letter. Maybe I can replace C with C. I come here, ABC, and I go to the next position, that is null. That forms a base case. I come back to the previous call, and from here I come back here, and from here I say, okay, replace B with C. It becomes ACB, and I make a recursive call on this one. Then I say, okay, maybe B with B, ACB, and I make a recursive call on this one. Okay, I come back, I come back, and I come back. Now one thing to note is, when you're coming back, and if you're maintaining the original array, if you're not duplicating your array every time, you're having the original array, then at this particular point your original array would have changed. Okay, so you had ABC, you changed it to ACB, and when you're coming back, if you're doing modifications in the same array, because arrays are passed by reference, okay, instead of having ABC here, you will have ACB. You will actually have ACB, and that can actually cause a problem. Let us see, if we have ACB here, what problem it would cause. So we go here, it will have ACB, and next time what you do, you swap A with C, it becomes CAB, and from here you make a permutation like this, CAB, and you also make it like this, CBA. You come back, this original array is changed, it becomes CBA. You come back, this original array has changed, it becomes CBA. And according to the logic, what you were going to do next, you were going to replace first character with the last character. It would have become ABC again, and you would permute BC. Okay, it would become ABC, and you come back, it still remains ABC, and you do ACB, you come back, it becomes ACB. Okay. So we will see in the code, if we make this mistake, if we do not modify our array while going back, we will end up getting the wrong result. Okay, we will end up getting the wrong result. Okay, these are not the correct outputs. We are getting these two outputs repeated. Okay, what we should do is, we should actually, while going back, we should modify, or we should restore our original array while going back. Restore our original array while going back, and this step is called as backtracking. Okay, we will see how we can implement backtracking in the code, but now let us see with backtracking logic what we can build. We have ABC, we say okay, replace A with A, then replace A with B, then replace A with C, and permute the rest of the stuff. Let us do the first call. We come here, we have this sub problem, replace B with B. We come here, we have this sub problem, it is too small, it becomes ABC. We come back, it is ABC. We come here, we go here, we replace B with C, it becomes ACB. We have this, we have this. Now we go back, we say okay, we replaced C with B, sorry, we replaced B with B, so we replace again B with B. We come back, from this step to this step, what change did you make? You swapped B and C, you do the swap again. Okay, you do the same swap again to restore the original array. Okay, so let me just say what you did. You did a swap of A1 with A2. Okay, you do this swap again and you will get the original array while going back. Okay, so what it becomes, it again becomes ABC. You go back, it again becomes ABC. Now what you do, you replace A with B, you make a call on here. What do you do, replace B with B and B with C, it becomes A, B and C. This call, it becomes A, C and B. Okay, and the next call will be A, C, B, A, B, C. Sorry, this should be like, I just made the wrong diagram here. This should be BAC, and it becomes BAC, and it becomes BAC. You go back, it is still BAC. You come here, A gets replaced with C, it becomes BCA. You make another call, it becomes BCA. you hit a base case, you print the answer also. Okay, every time you hit the base case, you have the permutation ready that you can print. You go back, you go back, you go back, and while going back, okay, so every time you go back, you undo the changes that you have made while coming to this step. Okay, and again you go back, you come here, a get replaced with c, it becomes cba, cba, and cab, go back, it becomes cba, you go back, it becomes abc. Okay, so every time you hit the base case, you get the right permutation. Okay, so this is how we are going to implement recursion along with a backtracking step to find permutations in the next video. Let's see how to write it in the form of a code. Hi everyone, so now let's discuss another problem. It's generating brackets. Very interesting problem on generating strings. We need to write a function to generate all possible strings which contain n pairs of balanced parentheses. So we can use these opening and closing brackets to generate strings which contain n such pairs. Okay, so for example, if n is 2, we know we only have two such pairs, and these are the two pairs. Okay, so input will be a number, output will be these strings. Okay, so let's see one more example. Also, you cannot generate something like this because it's not a valid expression. Okay, or like this, these are not valid ones. So if n is 3, then we have 5 such pairs, and you can verify that all of the parentheses are balanced. That means opening is matching with the corresponding closing bracket. So one thing to observe is if you have input of length n, or if input is 3, you need to fill 6 places. Okay, so can we apply the recursion funda to solve this problem recursively? How can we think recursion in such problems? So that is what we want to learn. So the idea is similar. What you can do, you fill one position with maybe an opening bracket or with a closing bracket, and you make a recursive call for the remaining part. Okay, now there is one problem. Okay, all the combinations are not valid. Okay, for example, a string cannot start with the closing bracket. So there are some rules that we need to think of while placing these brackets in the corresponding positions. Okay, so this is true. We can use recursion. We can fill for an index I, or fill at a starting position and make a recursive call for the remaining sub problem. That is true. Okay, so what are the rules we should keep in mind while filling these? So the first rule is, whenever you are placing a opening bracket, or whenever you are placing a closing bracket, we must have some opening bracket which has come before the closing bracket. That means if I'm making a string like this, I want to put a closing bracket here. Okay, can I put a closing bracket here? The answer is yes, because we have till now, we have 3 opening brackets, and closing brackets till now is 0, so we can put this closing bracket. Okay, maybe I go to the next position, I put a closing bracket here, I go to the next position, I put a closing bracket here, I go to the next position. Can I put a closing bracket here? The answer is no, because we had 3 opening and we had 3 closing till now, so we cannot put a closing bracket here. Okay, so let us say the value of n is 4, so in that case we will not put a closing bracket here. Okay, although we have both the options, but putting a closing bracket does not follow the rule that closing should come after opening bracket. Okay, so this is wrong. So can I put an opening bracket here? The answer is yes, I can put an opening bracket here. I go to the next index. Can I put a opening bracket here? The answer is no. Why? Because the count of opening bracket must be less than n if we want to place an opening bracket. Okay, so if you have placed 3 opening brackets and n is 4, then you can add 1. But if you have already placed 1 2 3 4 opening brackets, you cannot place one more opening bracket. Okay, so ultimately you will try placing a closing bracket. Can we put a closing bracket? The answer is yes, because opening is 4, closing is 3, so we can put a closing bracket here. So what I'm trying to say, you try to put both opening and closing, but one of these rules may restrict either placing an opening bracket or placing a closing bracket. Okay, so in order to just to simplify these rules, the count of close should be less than the count of current opening brackets, then you can place a closing bracket. And for opening bracket, the count of open should be less than the number of brackets you can place, that is n, then you can place an opening bracket. Okay, so these two are independent conditions. Okay, we have to check these two conditions independently. If one of these or both of these conditions are true, then you can place the corresponding brackets. Okay, so this is what we are going to do. Now let us try to solve this for a small example. Let's say we have n equals to 2 and I need to fill 4 positions. Okay, so in the beginning, can I put a closing bracket here? The answer is no. Can I put a opening bracket here? The answer is yes. We put an open. We make a call on this part. We are here. Can we put a closing bracket here? The answer is yes. Can we put a opening bracket here? The answer is yes. So both of the conditions are true because opening count is 1, which is less than 2, and closing count is 0, which is less than 1. Okay, so we will make two calls, one for the opening bracket and one for the closing bracket. So we make call like this, and now we are left with this sub problem and this sub problem. So what we do here, can we put a opening bracket here? The answer is no. Can we could put a closing bracket here? The answer is yes. So we put a closing bracket here. We come here. Can we put a opening bracket? The answer is no. Can we put a closing bracket? The answer is yes. So we get this one. Okay, so we get the first output. And what about this? So opening is 1, closing is 1. Can we put a opening? Yes. Can we put a closing? The answer is no. So we can put an opening bracket here. Can we put a closing? No. Can we put a opening? No. Can we put a closing? Yes, we can put. So this is the second output that we get. Now you can see this is actually a brute force algorithm. Okay, and we are using recursion to build this brute force logic, and in this logic we are adding some conditions to restrict the branches that are not valid. Okay, we are not going to into branches that lead to wrong output. Okay, so we are actually doing some kind of tree pruning here. Okay, so this is the way to solve this particular problem, and in the next video we will see the implementation. That's all. See you guys in the next video. Hi, so let's discuss the implementation for generate brackets problem. So what we are going to do, we are going to write this function that will take a empty string that I'm calling as output, and during recursive calls this output is going to get generated, and every time we hit the base case we will print this output. Okay, so we get the output, we get n, we get how many opening brackets have been there till now, how many closing brackets we have, and what is the current index. So if n is 3, so I will fill 2n positions in this output array. So once you are reached this point, you can say okay, the string is full, and we can print it. So that will form our base case. So I denotes at what index I am. If I equals to n, that means we have completely filled this output array, so we output it and we return. Okay, otherwise we have two options. We can place a opening bracket at ith position, and we can also place a closing bracket at a ith position, but there is a condition. If the count of opening bracket is less than n, then we can put a opening bracket. So let's see. So in your output you add a opening bracket like this, then you pass in n, count of open will become open plus 1, count of close will become close, and I will move to the next index I plus 1. For the closing bracket, if count of close is less than count of open, you can call generate brackets output plus a closing bracket n, and then we have open and count of close will be close plus 1 and I plus 1. That's it. Let's build the code. Let's try to run the code, and let me say I have 3, I get these, which is correct. I have 2, which is correct. I have 5. These are also correct. Okay. So let's just verify. Yes, this is a correct output. Now, one possible mistake that people can make is this. So let me just tell you what I am doing here. Okay. So I am in the beginning, the output is an empty array. Okay. So when I make a recursive call, I modified this output array. I say, okay, in my output array, add this opening bracket. This call is not made. From here, I make maybe 2 calls because both of the conditions are true. So I put another opening bracket, and in another call I say the output is like this. Okay, so this is the output that is being received by my new function call. Okay, and this works well. Okay, this is completely fine. So one thing that some people may do, instead of doing it like this, people may do it like this: output plus equals opening bracket, and they will send the output. And people will do like output plus equals the closing bracket, and they will send the output. Now this will lead to wrong answer. Let us see how. Okay, so if I now run this code, maybe I give n3, you can see this is not the correct output. Now what is the difference in writing code like this and the way I have written? Okay, so now what you're doing, you are in this call. Okay, you said, okay, in my output array I will add a opening bracket. You said, okay, add an opening bracket and give it to a new function that receives like this, and from this you make another call in which you have already added a opening bracket. So you add another closing bracket here and you give it to this function also. Okay, now this will lead to wrong answer. Okay, or from here you add a opening bracket and then you add a closing bracket and you give it to a new function call. Now this is not going to be true because you're not removing this one and you're adding actually 2 brackets in a single function call. You're adding opening followed by closing, which is incorrect. We want to add this closing in place of a opening bracket like this. Okay, we want to make it like this, not like this. So this is actually a mistake. We are modifying the same output array which has been already been modified at this particular point. Now if you want to fix such kind of a solution, one way we have already seen. Another way to fix this is you remove the last character that you added by using maybe a pop back statement that will undo this statement. Okay, so this is also called as backtracking. We, while going back from this function call, we can actually remove this opening bracket and clear our output. So we can do this, and you can see if I do this fix, then my answer is correct. Okay, so either use this way or the other way. In this way we are modifying the same output string, and in the previous way we are sending 2 modified copies. Okay, so although this is also a copy, this is also a copy, but these 2 outputs are common. Okay, these 2 outputs are common. That's why doing this pop back undoes this operation, and then we are able to get the correct answer here. But in the earlier implementation that we have seen, what you can do is so we have one output array and we are modifying it in 2 different ways before sending to the next function. Maybe once by putting a opening bracket here, and once by putting a closing bracket here. Okay, so this is also coming from somewhere. So this is also correct. We are sending this as a output, this as output, and since we have a string object, it is passed by value. Okay, passed by value. We are making 2 copies of this particular string, and that's it. So I hope you really understood the logic and you will avoid potential pitfalls that we have discussed. That's all for this lecture. Thank you. Hi, so now we are going to talk about an interesting problem which is known as n queens problem. So let's understand what this question is. So it's a problem of placing n chess queens on an n cross n chess board so that no two queens are going to attack each other. Okay, so we are given a n cross n chess board. For example, this is n equal to 4. So yeah, so what we want to place 4 queens on this chessboard so that no queens attack each other. Okay, so n can be 8, n can be 7, it can be 11. So it's a variable. So we are given input n, and in the output we need to print this configuration of the chessboard. Okay, this is what is expected in the output. So now if you look carefully, in this configuration no queen is going to attack each other. Okay, so if you know about a queen can move along a row, it can move along a column, or it can also move or attack along a diagonal. Okay, so if you see all of these, if you talk about this diagonal, this queen is not going to attack anyone. Okay, in each row there is one queen. That is another observation you can have, and it's not going to attack anyone in the row, it's not going to attack anyone in the column. Similarly, for this queen, the diagonal row and columns are empty, and for this queen also there is nothing, no queen that it can attack, and similar for this one as well. Okay, so we need to come up with a configuration that satisfies these constraints. Okay, so again you can see it is about finding an optimal configuration that satisfies these particular constraints, and we discussed that backtracking can be used to solve these kind of problems. So let's see how we would solve this problem, and let's try to come up with a logic. Okay, and there could be different variations of this problem. So a common variation could be print any one configuration that satisfies these requirements. Okay, another variant could be print all possible solutions of this particular problem, or another could be instead of printing the solutions you can simply count how many solutions exist for a given problem. So we are going to look at all these variants one by one, and what are the changes we need to make in the code in order to make them work. So let's see actually what we can do. So let's see. So let's assume that we have a board. We have a n cross n board, or a 4 cross 4 board for now, and we will try to solve this problem. Okay, so what is the idea that, so firstly we need know that in every row, so let us fill this grid row by row. So in every row there would be one queen. Okay, so one queen per row. So what we need to do, we need to finalize at what index the queen should be placed in the ith row. This is what we need to think. So what may happen is, yeah, so let's see. So as we discussed, we need one queen for every row. Okay, so we need one queen for each row. So now let us try to start fixing queens in each row. So what I will do, I am starting at 0th row, and I will say, okay, let me place the queen in the first column and let me try to solve the remaining sub problem. So now what is the remaining sub problem? The remaining sub problem is actually this grid. Okay, this is the remaining sub problem. So what we can do, we can try to solve the problem for the next row, that is I equal to 1. So what we will do, we'll say, okay, let us go and try to place a queen at an optimal column in the current row. So what I will do, I will say, okay, I go here, can I place a queen here? The answer is no. Can I place a queen here? The answer is again no. Can I place a queen here? The answer is yes. So I will place it, and I will say, okay, for this row I am done, because when I place the queen at this index, I don't have a queen in a column, I don't have a queen in a diagonal. Okay, I don't have a queen in the row, because for row we don't need to check, because we are not placing any queen in the same row. So this is actually done. Now what we will do, we will go to the next row and we will say, can I place a queen here? The answer is no. Can I place a queen here? The answer is no. Can I place a queen here? The answer is no. Can I place a queen here? The answer is no. Now this row tried all possibilities in I equal to 2, and we could not find that this row can be solved. Okay, so now what we will do, this row is going to tell the previous call. Okay, so this was the first call, this was the second call, and this is the third recursive call. So the third recursive call is going to tell the parent call that there is something wrong with your configuration, go and correct it. So what we are going to do, we are going to backtrack, we are going to go back to the previous row. Okay, so when we are going back to the previous row, this function call is over and we don't have any information about this row as of now, and we will say, okay, whatever you were trying, okay, so this row, this function call will maintain till what column I have already tried placing the queen. So it will know, okay, at j equal to, let's say, 2, we had tried, and now this value of j will move to the next index. Okay, so what we will do, we come back to this row and we will erase our action that we did. So this step is actually going to be a backtracking step. So we are going to remove this queen from here, and we are going to say this is not a optimal location, maybe you should place a queen here. Okay, so we place a queen here. Now again, what we are going to do, we are going to again call on the next row. So can we place a queen here? The answer is no. Can we place a queen here? No. Can we place a queen here? No, because it's going to be attacked by this queen. Can we place her here? Answer is no. Again, what is going to happen? The third row is going to tell the second row that, okay, this configuration is not possible, there is something wrong that you have done. Okay, so it's going to, let's go back, let's backtrack, and again we are coming back here, and in this row we have already seen that, okay, the fourth column is also not suitable for the configuration. Okay, so what is going to happen, we have tried all possibilities in this row. When we have tried all possibilities in the current row and the solution is not possible, we are going to send a message to the previous row. So that message is false. Okay, that this is not possible, this is not possible. This false we will send by maybe having a return type in the function, that may be a boolean. So what is going to happen, each row is going to try some configuration, and if it is not successful, then it is going to return false or true to the previous row, depending upon the configuration was successful or not. So we will return true if the remaining grid is solved. If the remaining grid is solved, we will return true. If the remaining grid is not solved, we will return false. That is the whole idea of passing this message. So what we are going to do, we are again going to going back in the first row, and we are saying, okay, let us, the first row knows what is the state. Okay, what is the state of the variables that we have seen. Okay, that means the first function call will actually store that, okay, I have already seen till the column number 0, so let me try the next column in the first row. What it will do, it will say, okay, let us remove the queen from the 0th index, and maybe let me try to place a queen at the first index. Okay, it will say, okay, go and try and solve the remaining sub problems. So it will make a call on I equal to 1. So in this row, what we will do, we'll say, okay, this location is not possible, this location is not possible, this location is not possible, because if you place at these locations, it will be attacked by this queen. Okay, so what we will do, we'll place a queen here and we will make a call at I equal to 2. And you're going to ask, okay, next row, go and try to solve the entire subgrid that is pending and tell me an answer, true or false. If it is true, well and good, I will tell everyone, my parent, that the grid was solved. If it is false, then I need to try something different, or maybe the solution does not exist. So what we will do is, okay, let us place a queen here. Is it possible? The answer is yes. If you place a queen here, it cannot be attacked by these two queens. Okay, and then we don't need to do any work in this row. Okay, we will just jump to the next row, I equal to 3. Let us try to place a queen here. Can we place it? No. This will be marked as invalid. Can we place a queen here? The answer is no. Can we place a queen here? Yes, because we don't see anything in the diagonal. and yes, the queen can be placed here, okay, and it is going to make a call on I equal to 4. So as soon as your I becomes equal to n, what you are going to do, you are going to return true, okay. So who is going to return true? So the you made another function call, okay, let us go and complete the next row. So you made a call from here to here, so this becomes a base case. In the base case, you check if I equals to n, that means our problem was solved. We are not going to make any further calls. We are going to return true. So this row gets to know that the remaining problem, which is an empty grid, was solved, and I should tell my parent that the remaining grid is solved. So this will return true. So this true will be returned back to second row. This will be returned back to the first row, and this will be returned back to the main. Okay, and finally, main will get to know the solution of this problem exists, and in the base case, when the base case was hit, we had the state of the board. And we could easily print this particular solution. Okay, what we will do, we will print this solution, okay, and we are done. That's what we are going to do. So this is for the problem where we need to print one configuration, okay, so where we need to print one configuration, or we need to check whether the configuration is possible or not. So this code will serve both the purposes, and we can solve this problem by this, okay. So in the next lecture, I will write the code. Along with it, we will try to understand how that code is going to work. So see you in the next video. Hi, so now we are going to look at the implementation of n-queen problem. So first of all, we will create a board. So let's say we have a maximum of 20 cross 20 board. Because for higher inputs, this code will not run because the complexity is huge, and maybe after 11 or 12 or 13, this is going to be very difficult to be processed in a 1 second. Okay, so we have a small board, let's say of 20 to 20. The input would be maximum, let's say 13 or 11. And we will take input the value of n. And now what we are going to do, we are going to create a function, let's say solve n queen, and let me show it to you. So we will have a boolean function, let's say solve n queen, and here we are going to give the value of n. We are going to give the board, and we are also going to give the current row in which we are currently are, okay, because that is needed. And now we discussed about a base case, and we also discussed about the recursive case. In the recursive case, we said we will try to place a queen in every row, okay. And in the base case, we said that if we reach a row that is equal to n, that means we are done. In this case, we will print the board and we will return. We will not make any further calls, and we will terminate our recursion from that particular base case, okay. So maybe we can create a function void print board that is going to take input n and board, and yeah, so it is going to loop over all the rows, and it is going to iterate over all the columns. Then we are going to say cout board of ij, okay, followed by space and followed by handle. So now in the base case, what we need to do, we simply need to call the method print board, and we give n and the board. That's it, we are done. But in the recursive case, we need to try every column. So what we will do, we will say, okay, let us say the column starts from 0, column is less than n, and we do j++. And here what we will do, we will say I need to check whether the current position is safe or not, whether the current ij is safe or not. So what does it mean by safe? Let me just tell it to you. Let's say this is our grid, and let's say we are currently in the ith row, okay. Let's say this is the row in which we are putting a queen here. Let's say this is where we are putting a queen. So if I want to place the queen in the ith row and the jth column, what I need to check? I need to check that there is no queen in this particular column and there is no queen in this particular diagonal and there is no queen in this particular diagonal as well. So these are the three things where we need to check. Now you may ask why we are not checking along this direction and this direction. So this is because we are putting only one queen in a row and we are not checking here because this part of the board is yet to be filled. Okay, this part is yet to be filled. So there is no point of checking here. So we'll make a helper method that will check whether a queen is present in these diagonals or on this column. So what we will do, we'll define this method and let us assume that this method is can place. Okay, so if a queen can be placed in the board of size n at index I and j, only then we are going to place a queen. Okay, so how do we place a queen? Since it is an integer board, maybe we can mark that location as 1, rest everything is 0. So if that queen can be placed, then place it, then we can say board of ij equals 1 and check for the remaining sub problem. Okay, so bool success will denote whether the remaining board could be successfully solved or not. So we can call solve n queen and we give what we give n, we give board and we give the row number that is now I plus 1. Okay, and now this success will tell us what to return. Okay, so we will assume that okay, this row is calling to the next row to check whether it was successful in solving the remaining problem or not. This success, if it is true, then you will return true and this position will be freezed. But if it is false, then you will try out the next position for the queen. If it is false, you will try out the next position, and if it is false and you move out of this particular row, then you will return false to the parent. Okay, to the parent function call. So look carefully. If you got success from the remaining grid, then you return true. Okay, I'm not writing else return false. I'm not writing like this, else return false, because this is not that we are going to do. If it is not success, then this loop will take j to the next location, and what you need to do, if it is not true, you already placed a queen here, but this is not the right location. Okay, so you need to backtrack, you need to update, you need to remove this. Okay, you made a function call and I said backtracking code will come after the function call. That means you made a call here, this call returned false. That means you will update this queen index, you will put it here. Okay, so let us make board of ij equal to 0. That means we are removing this queen from here, and in the next iteration of this for loop we are going to j equal to j plus 1 and we are putting a queen here. Okay, we are putting a queen at this particular index. Okay, we were putting a queen here, and then again we are going to make a call here and check for success. Maybe let us assume that this time we got a success. We are going to tell the parent call, okay, we got successful, and let's not make any changes and let us propagate true back to the main. So this will give true, 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 and so on. So this is how this problem is going to get solved. But now there is still one case that is left. That case is when you have finished the entire row and you could not place a queen successfully. That means if you somehow come out of this for loop, that means you will come out of this for loop if and only if there was no position in the row that could satisfy the constraints. Okay, that means there is something wrong with the parent, and you should tell the parent call that you need to update your location. So if this row returns a false, then that means something will get updated in the parent call. Maybe in the parent call the queen was here, then you will say let us remove this. So this line of parent call will get executed, and in the next iteration j will take a next value and you will place a queen here, and again you will make a call on this row. Okay, and again you will start from 0 till n minus 1. Okay, so this is what is going to happen. So this is the complete backtracking code for the n queen problem. Now one thing is left, we need to implement this function can place board n ij. So let's implement this method as well. So what we are going to do, we are going to say so we are going to say bool can place, and I get the board, I get the n, I get the x comma y where I am placing a queen. Okay, so we need to check for the column first. So in the same column, for int k equal to 0, k less than, let's say, x, k plus plus, if board of k comma y, if this is equal to 1, we can return false. Okay, we can have left diagonal and we can have a check for the right diagonal as well. So what I'm going to do, I'm going to copy the variable, the coordinates in a variable ij, and I can check while I is greater than equal to 0 and j is greater than equal to 0, if board of ij, if this is equal to 1, then that means a queen is present and we should return false, and we should update I as I minus minus, j as j minus minus. And let us do the work for the right diagonal as well. So I is equal to x, j is equal to y, and I can put a loop while I is greater than equal to 0 and j is less than n. So don't worry, I will explain these conditions. If board of ij, if this is equal to 1, then we can say return false, and we can do I minus minus and j plus plus, and if none of these conditions is false, then we should return true. That means we could not find a queen in the column left diagonal or in the right diagonal, and we should return false. So let's see what we have done in the can place method. So we have this board, we have this row, we have this column, and here we have this as a queen. First we checked k equal to 0, k less than x. This is x row and the yth column. We are iterating from 0 till less than x. We are iterating over these rows, and the column is fixed as y. So we are iterating over this entire area. And if we could see there is a queen here, we would simply return false. Oh, sorry, this one. Then we are iterating from I equal to x, j equal to y, while this is greater than equal to 0. Basically till this particular point. We are saying we should not go beyond 0 0, because that would mean indices that don't exist in the board. So what we are doing, we are saying, okay, we have this cell xy, so we want to go to diagonally one step back. So that is, if this is ij, then this is I minus 1 and j minus 1. Then again we go one step back by doing I minus 1 and j minus 1. So this loop allows us to move in this particular diagonal. Similarly, the right loop allows us to move in this particular diagonal. Okay, so when we are going right, we are reducing the number of rows, but we are increasing the number of columns because we have to go towards right. But in the left, we have to reduce the number of columns as well. We are checking if we could find something in the left diagonal or in the right diagonal. We should return false. Okay, we should return false. And if all of these conditions, none of these conditions returns a false, we are going to return true. That means there was no such queen, and we can easily safely place a queen here. Okay, so this is the can place method. So quite a bit long code. So maybe let's try to solve n queen, and we give the value of n as n, and we give the board as board, and the starting row we can give I as 0. Okay, and let's give some input, maybe a 4x4 board, and let us try to, okay, we got, okay, we should return true, that okay, we could solve this problem. Okay, we have this as well. All right, so you can see we got one possible configuration, and if we look carefully, then this configuration looks like a valid configuration. Okay, this looks like a valid config. So this is what we had designed, q q q and q. So this is q q q and q. So yes, it exactly matches this output that we have derived, and that means this code is working perfectly fine. Okay, so a quick recap of what we have done. So this part of the code is the main part, and what we are doing here is that is something that you need to look at. So for every row we are trying to place the queen in every column. Okay, so here we are saying, okay, let us go to every column, and in every column there could be certain locations which are invalid. We discard those. There are certain locations which are valid for now, but maybe they're not part of the solution. So what we do for those configurations, we first place the queen, then we check can we solve the remaining sub problem. The remaining sub problem tells whether it was successful or not. If it was successful, we tell the parent calls that okay, the problem got solved, just propagate a true back to the main, and main gets to know, okay, the problem is solved. But if the problem is not solved by using that particular row and column, let's say we are at particular row I and we are at particular j, then we say okay, let us remove the queen from this particular j and let us make j as j plus 1, and we put a queen here. Okay, so this is like putting the queen and this is like removing the queen. And even after completing the entire row, okay, so this is after finishing entire row, if the queen could not be placed, then we will tell the previous row something is wrong with your configuration, go and update it, and this is a signal to the previous row. Okay, this is also a signal to the previous row, but the false signal should be sent after the loop. Okay, after you have tried all possible configurations, after all columns have been checked in the current row. Okay, so that's all for this lecture. I hope you really understood this problem. Thank you. Hi everyone, in this lecture we are going to discuss a slight modification to our previous problem, that is the n queens problem. So sometimes you might be asked, okay, instead of printing one configuration, you tell me the count of configurations. Okay, in how many ways you can solve this problem. So what we did in the previous call was we were exploring the search space. Okay, and each node in this search space represents a state of the grid in which a certain queens are placed. So what we did, we said okay, once we reached a valid state of the grid which satisfies the given constraints, we said okay, we'll return true and we will not make any further calls. Okay, this is what we did. But if you need to count all possible configurations, we don't need to stop whether the configuration was found or not. Okay, basically we need to make some changes in this part. Okay, because this is the part that is stopping the further calls. Okay, this is stopping the further recursive calls. But if you want to find out all possible configurations, then you should not stop. Okay, so what we will do, we'll make some changes in the code. I will tell you. So firstly we will make it as maybe int. Let us, we want to return the number of ways, so maybe the return type is we'll change it to int, and whenever the base case is hit, okay, let me just comment out print board. So I'll say okay, let me return 1, because there is one way in which we could hit this base case. Okay, this is hit only if the configuration was successful. Okay, otherwise we could not reach I equal to n. Okay, in the recursive case, what we are going to do, we'll still do the same thing. We'll try to place the queen in every column. We will try to check whether the position is safe or not. If it is safe, we will place it. And here we don't need to check whether the remaining board was solved or not. Okay, so what you can do, you can assume that your answer is currently 0, you're starting from the 0th row, and the answer denotes the number of ways. Okay, maybe the number of ways to solve this problem is 0. And what do? You basically ask the next row in how many ways you can solve this problem. Okay, so basically you have something like this. You assume that for the current row, I am assuming that my answer is 0, and you ask this remaining grid in how many ways you can make up the remaining configuration if I fix a queen at this particular point. Okay, this is what we are doing. We are saying, okay, let us assume that the answer, the number of ways right now is 0, but tell me in how many ways you can fill this remaining grid, and that I will add to the number of ways. Okay, so I will say we actually don't need this one, we don't need this part. We'll say, okay, ways plus equals to solve queen. Okay, now this is an important step. So what is going to happen when you place a queen here? Maybe the remaining board can't be solved. Okay, maybe the remaining board can't be solved, and maybe it returns a 0 here. But maybe when you place a queen at this particular index, let's say you place a queen at this particular index, then maybe the remaining board returns 1. So you will add 1 to the base. Maybe then you try to place a queen at this index, the remaining board again returns a 1. Maybe you add 1 here. Maybe you again place a queen here, the remaining board returns a 0 here. Okay, so maybe you will get, okay, there are 2 ways in which I can solve for this part of the board by putting queens at these locations. Okay, and it is also possible for some bigger board. Maybe the remaining board tells us that this subgrid can be filled in 8 ways. We will add 8 to the answer that you are forming for this particular row. So each row will form its own answer. Okay, each row is going to form its own answer, and when you're going to total up, you're going to total up the answers for all the columns for a given row. We are going to add them up, and we are going to return back to the main. Okay, this is what we are going to do. So this is exactly what we are going to do here. So we have already made the changes. Okay, so we assume that we don't know in how many ways we can solve the problem. We assumed our answer as 0 for every column. Whatever is the number of ways, we computed using a recursive call, and every time you hit a base case, you're going to get a 1. Now why this will work is because, let's say, from this board you make multiple calls. Okay, if you have 4 columns, you're going to make 4 calls. Maybe one time queen is here, another time it is here, another time it is here, another time it is here. Okay, so whatever these boards are going to return, maybe x, y, z and w, you're going to add them up, and this will actually go recursively. And this time I is 0, this time I is 1, this time I is 2, and this will happen till then. Okay, so in the some of these calls will lead to the base cases, and those some base cases would return 1, and some will not lead to base cases. Okay, some calls will not lead to base case. So in those calls, maybe the number of ways is 0 and you're returning ways as 0. So in some calls, this answer might be 0. Okay, so the valid base cases would return 1, and in the end you are actually summing up these ones, and here you will get a final answer 8 or 92 or whatever it is. Okay, all right, so maybe we should try to run this code. We should give change this output, see out the number of ways is to solve the n queen problem is this, and here what we are doing, yeah, we are returning an integer. So let's run our code for n equal to 4, and you can see we have actually 2 ways, and I will tell you what are those ways. Okay, I will tell you what are those ways. Let us run the for n equal to 8. For this the answer should be 92. So let's see. Yes, we are getting the right answer. Okay, so let me go back here and let me tell you why this answer is 2 and how this code is working. Okay, so right now we are now discussing print all config. So the work we have done till this particular point in the explanation video, I'm going to just start on the top of that. Okay, what we discussed, first time we found this particular solution. Okay, so first time in this particular row we placed a queen at this location, but for this queen we got the number of ways as 0. Okay, so let us assume we already got an answer of 0 because no configuration was possible. But next time we placed a queen here, okay, and we made a call on this row, and for this row we are already on the last column. So this column is going to return it is going to be like this: 0 plus 0 plus 0 plus 1. You could only found out one way when you placed a queen here. Okay, so it is actually going to return 1 to the previous row. Now what is going to happen? So this was the first solution that we found out. Now we are not going to stop after finding this particular solution. What we are going to do, we are going to say, okay, all right, we are done with the solution. Let us backtrack. Let us remove this queen from here, and let us try to place a queen here. Okay, so here you can't place a queen. That means something is wrong. It's not a valid state. We will go back. So this will actually return a 0, and we are at this row now, and we say, okay, let us try to change the location of this particular queen. So we have already tried. Can we place here? The answer is no. Can we place here? The answer is no. Can we place here? The answer is no. So we'll go back and we will try to remove this queen. And can we have already tried this one. So can we place here? No, the answer is we can't do anything else here. So what we will do, we'll again go back and we'll try a new configuration. Okay, so we will try to place a queen instead of. So although this was a successful configuration, we have already tried. We are going to remove it and we are going to start afresh. Okay, so I should have removed these crosses, and we are trying at this location. So if we place a queen here, can we do something? The answer is, can we place a here? Yes. Let's go to the next row. Can we do something here? The answer is yes. Let's go to the next row. Can we place a queen here? The answer is yes. So we found out another configuration. Okay, so here it is going to make a call on the base case. Base case is going to return 1. So ways for this is going to be 0 plus 1 plus, if you try to place a here, it is not allowed. You try to place here, it is not allowed. So it's going to be 0 plus 0. Okay, so it is going to tell the previous row there is one way that this row could have been solved. Okay, so this row can be solved in one way. This will tell us 0 plus 0 plus 0 plus, for this location we have one way. So 0 plus 0 plus 0 plus 1. So this will tell 1 to this call, and now this row will again try to place a queen here, which is not allowed. Here it is not allowed. Here it is not allowed. So it will be again 0 plus 0 plus 1. So it is again going to return another 1 here. So it would be like 0 plus 1 plus 1 plus. Now this row is going to try to place a queen here and do the work, but it is a symmetrical case. So it's again going to be 0. So you're going to get actually two ways. So effectively, the two ways that we are getting, they are mirror images of each other. Okay, you will see the configuration is mirror of each other. So I will just print this board for all the configurations by calling this method now, and I will show you the answer that, okay, these two configurations are actually same. Maybe we should call this solve n queen and then try to run. Okay, so if you now look carefully, that these two configurations are actually identical. They are mirror images of each other. Okay, so these two are mirrored, right? So that's why we are getting these two ways. So I hope you really understood this problem. So in every recursion problem, you need to see what to build and how to build. Okay, so here what we did, here we made this logic that for every row that is going to return some answer, the total number of ways would be the sum of each column. Let's say this has S1, this has S2, this has S3, this has S4. So the answer for row S1, S2, S3, S4, row I would be sum of S1, S2, S3, S4, which in turn depends upon the number of ways returned by the remaining sub problem by placing the queen at the jth column. Okay, that's what we are doing. Okay, so I hope you really understood these two variations as well, how to count all possible configurations and how to print all possible configurations. Okay, so this is something that we learned. Sorry, now I have added a very large number. This kind of a code will not work because the complexity of this code is going to be exponential. Okay, you can see it is going to take a lot of time, and we are going to get a TLE kind of a thing. Okay, so it's not going to run, but for a small value we can actually run this code. Okay, so you can see we are getting the answer for a 8x8 grid, and there are 92 such combinations which are possible. So one last thing was the complexity. What is the complexity of this code? Okay, any guesses you want to make? So what we are doing, for every row, what we are doing, we are picking one position. Okay, so we are picking one position in NC1 ways, and for each of these positions we are picking NC1 position from here, NC1 position from here, NC1 position from here. So this is nothing but n into n into n. How many times we have n rows? N times. Okay, this is n raised to the power n. Okay, which is a very large exponential complexity. Hence this code will not work for larger values of n, and we can't actually solve for larger values of n. Okay, in a limited time. One small thing that you might be asked is there any tighter bound on the complexity? So one thing that we can think of is, once you have placed a queen in this particular row, you know that you will never place a queen in this column. Okay, so this this you can skip in like order one time, and maybe you are trying the remaining n minus 1 combinations. Okay, so if you have n ways here, for the next row you have n minus 1 ways to pick the queen, for the next you have n minus 2. Okay, so in some sense it can be written as n into n minus 1 into n minus 2 into 1. So you can also say that order of n factorial, which is also an exponential complexity, this is a slightly tighter bound than order of n raised to the power n. Okay, so this is also fine. You can choose this as an option if you get a MCQ kind of a question as well. So that's all for this lecture. Thank you. Hi everyone, welcome to another lecture on problem solving, and in this lecture we are going to solve a very interesting problem, which is this Sudoku puzzle. Okay, so in this question what we are given a partially filled Sudoku matrix. So it's a Sudoku game, and we need to write a function to fill the empty cells, and we should follow the Sudoku rules while filling the cells. Okay, so for the input part you can assume that all the cells which are not filled, they will contain the value 0. So you need to replace these values which are 0 with some valid value. Okay, so there can be multiple solutions possible. We want to print one possible solution. Okay, so let me give you a quick recap of what we do in a Sudoku. Okay, so if it is a 9x9 grid, then every row should contain the numbers from 1 to 9, and every column should also contain numbers from 1 to 9, and also every subgrid, which is a 3 by 3 subgrid in this case. Okay, so this subgrid, this subgrid, this subgrid, so they should also contain numbers from 1 to 9, and no number should repeat. Okay, so no number should repeat either in the row or in the column or in the subgrid. Okay, so if I give you one example, so maybe can you put 1 here? Maybe we can, maybe putting 1 may not create a valid solution. Okay, so we don't know. So what we have to do is we have to try all possible numbers at all possible locations. Okay, so this is what we will do. Okay, so we will do, let me tell you. Okay, so let us think in terms of a brute force solution, how we can try out all possibilities. Okay, so how we can try out all possibilities. Okay, so this is the only thing that we can think of in this case, and we will stop when we get one valid solution. Okay, so we will stop once we get one valid solution. So what you can do, you start iterating this grid from left to right or from top to bottom. So let us say we are going to go cell by cell, and let us stand here and we see this cell is already filled. Okay, so we will not modify the cells which are pre-filled. So we jump to this cell, it is again pre-filled, we jump to this particular cell. Now at this cell you have an option to place all the numbers from 1 to 9. Okay, so you will say, okay, let me place 1 and let me try to solve the sub problem recursively, and I will come to know if a solution exists or not. So how we can solve that sub problem? We can make a recursive call on this subgrid. Okay, so if the cell is I comma j, so that means we are making a recursive call on I comma j plus 1. Okay, so we are making a recursive call on the next column, and recursion will do its work. So what it will do, it will say, okay, let me try to place a number here, and while placing a number here, what we will check? First we need to check whether that number is valid or not. So can we place 1 here? The answer is no, because 1 is already there in the row. Can we place a 2 here? Maybe we can, maybe we can't. Okay, but by looking at this row, this column and this subgrid, we see 2 doesn't come. So let us place 2 and let us go to the next cell and try to solve the sub problem. So this will be the sub problem. Okay, so this will be the sub problem. Now these sub problems, okay, they are going to tell the cell from which we made a call whether this problem can be solved by placing 2 or not. Okay, so what do? You say, you check at given I comma j if a number can be placed, if a number can be placed. Okay, and what is going to be that number? So you will try for all the numbers, for number in the range 1 to 9. You check at a given cell if this number can be placed. That means it doesn't occur in row, it doesn't occur in column, and it doesn't occur in the subgrid. Okay, if it can be placed, then you place it. That means you say array of I comma j equals to that number, and you solve the sub problem. Okay, so you maybe say solve I comma j plus 1, and now this sub problem will tell you whether the number that you placed is the right number for the optimal solution or not. Okay, so maybe 2 might not be the best number, maybe we want to put 5 or 6 or 7 or 8 or 9, something else. Okay, so this function will tell you, okay, either this is going to be true or this is going to be false. You can make it a boolean function to tell whether the sub problem could be solved or not. Okay, if the sub problem could not be solved, you try the next number. If the sub problem can be solved, you return true. Okay, so what I will say, try next if solve return false. Okay, otherwise you can simply say return true. Okay, that means your problem could be easily solved. Okay, so return true otherwise. Okay, so try next basically means you go to the next step in the for loop and try to do the work for the next number. Okay, so this is how we are going to solve the problem. So I hope you got an idea. So the logic is very straightforward. The only thing is you need to think of corner cases. Okay, now let us also talk about base case. What would be the base case? Okay, so in the base case, you keep on going like this. Okay, one corner case, not the base case, but one corner case would be when you reach end of the row, you need to convert this call into this call. Okay, so you can put it something like this. If the column, that is j, becomes equal to 9, you go to the next row. That means you put I equal to 0 and I equal to I plus 1, and you put j equal to 0. So you do this step and you keep on going row by row this way, and finally you will end up at this particular row. Okay, so you will end up just after the last row, and if you reach this particular point, that means your problem has been solved. So your final case would be if I equals to 9, that is you have covered all the 9 rows numbered from 0 to 8. That means your cross the last row, then you can simply say return true, that this problem can be solved. Okay, and one final case could be like this: if you could not get any number. Okay, so if you have tried all the numbers that you have placed, you could not get any number, then what you will do? Okay, in that case you will say, okay, whatever number I have written, finally, okay, maybe you tried 1, it didn't work. Okay, let me just draw at this particular cell. You said, okay, let me put 1 here, it doesn't work. Let me put 2 here, doesn't work. Let me put 3, doesn't work. 4, 5, 6, 7, 8, 9, it doesn't work. Then what? Okay, so you have tried all the numbers here. Now what do you need to do? You need to go back and change some other cell. Okay, so in that case, if you have tried all possibilities at the current position, that means there could be some mistake in the beginning. Maybe you have put the wrong number in the previous call, or in the previous call, or in the previous call. You can simply say, whatever number I have placed, just make it 0 because it doesn't work, and return false. Okay, and return false. So this we will do after this loop. Okay, so that means yeah, so that means we are going to do the backtracking here. Okay, we are going to go back and do some corrections. Okay, we are going to go back and do some corrections. Okay, so this is a very high level logic, and I will again give you a quick recap of what we are thinking of, what we are going to do. So the idea is, you go to every cell, you place a number, you start with 1. If 1 can be placed, you place 1. If 1 cannot be placed, you place 2. Maybe 2 can be placed, but 2 is not the right number. So how you will come to know that? By making a recursive call on the sub problem. This sub problem will tell you whether 2 is right. If it says 2 is right, you tell its parent or the previous function call that, okay, this problem can be solved. Okay, if this says no, you cannot place 2 because I cannot solve the subgrid, then you say, okay, no, let me try with 3, but 3 cannot be placed. So you just skip 3 and you go with 4. You check 4 cannot 4 is not coming in the row, 4 is not coming in the column, 4 is not coming in the subgrid. You place 4, you make a recursive call. That recursive call tell you whether you could solve the problem or not. If let's say it's again says false, you put 5, 5 cannot be placed. You go to 6, 6 cannot be placed because it is here. You go to 7, 7 cannot be placed because it is in the row. You go to 8, 8 cannot be placed because it is in the column. You go to 9, 9 cannot be placed because it is in the subgrid. Now what? Okay, you still have a number 4 here, and you need to remove this number. You want to make it 0, and you need to go back. Okay, maybe you had an empty cell here, but if in this case it doesn't work, you will say, okay, return false. So this returns false here, this returns false here, this returns false here, and this basically tells the function that no such solution exists. Okay, so this is how it is going to do the backtracking, and this solution is going to really work well. So in the next video, let us see the implementation with the recursion and a backtracking approach. Okay, so thank you. Hi everyone, so let us go through the implementation for the Sudoku solver as we have just discussed. So what I have in this boilerplate is, I have the input ready. This is the matrix that I want to fill, and I want to replace all zeros with valid numbers, and this is the boolean function that I have created. If it would have been count the number of ways in which you can fill the Sudoku, I could have made the return type as int, but for now we are looking for only one solution. This bool will work fine, and we will stop backtracking once we found out the right solution. Okay, what we just discussed is, what we will do, we will try to move forward in the grid, and at some point we realize that, okay, we are not able to place a right number. So in that case we say, okay, we return false. That false propagates back, and maybe we filled a number here, we try to update that number, but it still doesn't work. So that again returns false, and at this point maybe we had placed 5, then we try to update it as 6 or 7 or 8. Maybe 8 is a valid number that we can place here. So what we do, we place 8 here, and we again make a forward call. Okay, we say okay, go and solve the rest of the puzzle. Okay, so this is how we are going to proceed. So just one correction, instead of going this in a zigzag manner, we are going in this particular manner. Okay, we are going like this, like this, like this. At this point, if problem happens, then we again backtrack in the similar direction. Okay, like this. So let's see how we can actually implement this problem. So let's go through the code. So first of all, I need to write some base case, some recursive case. So this is what I do for every problem. So let us think of the base case. So maybe I can say if I equals n, which is 9 in this case, we have a 9 cross 9 grid. And what we can do, we can say okay, we found out the solution, we can print the solution at this particular point, and we can return. Okay, and we can return. So it's going to be an easy one, and we are going to return true. If we find out the solution, we will print the solution later. That means we will print the matrix. And in the recursive case, let's see what happens. So in the recursive case, one case could be we are at the end of the row. Okay, so we can say if j equals n, that means we need to shift to the next row. We can say return solve Sudoku the same matrix, I goes as I plus 1, the column goes as 0, and n remains same. So if you are at this particular point, okay, so if you just cross the boundary, okay, so you want to shift to this particular point. So this is j equals 9, so you say okay, this is I comma j, so this becomes I plus 1 and j becomes 0. So this is what you do. So when this cell makes a call next, you say okay, return whatever is returned by the sub problem, which is starting at this particular cell. Okay, so this is what we do. So I hope this case is clear. And another case could be if the cell is already filled, if it is a pre-filled cell, so we need to skip the pre-filled cell. So how we can find that? If matrix of ij is not 0, okay, that means it is a pre-filled value. We do not need to do anything at that cell. So we just need to make a recursive call on the next cell. And it is possible that the next cell is also pre-filled. Okay, so in that case, we will again hit this case and we will make a recursive call to the next cell. Okay, so otherwise we are on the cell to be filled, and for the cell you don't know what is the right number, so you have to try out all possibilities. So you say for int number equals 1, number less than equals n, number plus plus, and now you need to check whether it is safe to place the number or not by looking at the row, column and the subgrid. So if is safe, I can make a helper method that will check if it is safe to place number at position I comma j, then only I will place that particular number. Okay, so how we are going to place that particular number? We are going to say let us try to solve this puzzle by placing this number at I comma j and making a recursive call to solve the sub problem. Okay, so this variable solve sub problem will be true if the remaining sub problem can be solved, okay, by placing this number. Otherwise, okay, let us see, if solve sub problem is true, we can say okay, return true. If it is false, then you can clearly see that this for loop will work. So let me just tell you what we are trying to do. Let's say we are at a particular cell. I say okay, let us place 1, but we see 1 is already there. I say okay, let me place say 2, but let's say 2 is already there. let me say, okay, let me place 3. Yes, 3 can be placed, so we place 3 here, and we make a recursive call on this part. Now the problem arises, maybe by putting 3 we cannot solve this grid. Okay, we cannot form a solution if 3 is present here. Maybe the solution should contain 5 here. What we do, this subproblem will automatically return false. Okay, and what we will do, this loop will work, and we will try to place 4 here. Maybe 4 is present here, we will skip it, we will place 5 here, and once we place 5, we make a subproblem, we make a recursive call, and let us say this matrix gets solved and we hit the base case, and in the base case we are going to print the solution. Okay, so whatever the values are there, they will be contained in this matrix, and we can just print that matrix. So we can return true if the problem is solved. Okay, if it is not solved, we return false. We try 6, we try 7, we try 8, we try 9. If it is still not solved, we make this cell as 0 and we return false to the previous calls. So this step is going to be called as backtracking. Okay, so we will write the backtracking step now. So if no option works, then what do, you make the current cell as 0. Okay, and you tell the previous call that you need to change something and return false here. Okay, so we go back, we again try something on the previous cell, we come to the current cell again. If it doesn't work, we again go back, we may again go back further, and so on. Okay, so this goes on like this. Okay, so maybe we come here, and at this point we go back, and maybe it still doesn't work, maybe we go further back, we try to change something here, then we again come here, we update these values, again we may get stuck, we can again come back, we can change here, and so on. Okay, so you don't need to dive into how this is working, but if you have an idea, if you can assume that this always works, then it will be easy for you to write code. Okay, so while writing code, you don't need to think how this backtracking is going to work if you are a new, or if you are a beginner in solving these type of problems. Once you have written the code, once it works, you can easily verify how this code is working or why it is working. That thing you can do very easily. Okay, so for beginners, I suggest try to break the problem in simpler cases, write the code, and then try to think what is your code doing, why it is working. Okay, so I know it's a bit tricky to explain, it's a bit tricky for the beginners to think, but this is the beauty of recursion and backtracking. You can solve complex problems very easily by writing just simple logic. Okay, and everything is done by this magical function, solve sub problem, which is indeed the function that we have written. Okay, so do it for one cell, and the rest recursion will do it for you. Okay, so this is the point that you need to keep in mind, how I handle for one cell. Okay, if I cannot fit any of these numbers in my current cell, what I will do, I will say, okay, just make it 0 and return false to the previous cell, and that's it. Okay, so now what we need to do, we need to write this function is safe, and it's going to be a pretty easy function. So let us quickly write the code for this one as well. So let me say bool is safe, I get the matrix, I get the coordinates, I get the number, I get n. So first thing is I need to check whether this number is present in the row or column. So for that, I can simply put a loop like this. I can check for row and column. So it's going to be pretty easy. So if I check if the number is either present in the row or in the column, I can say return false. And another thing we can do is we can check for subgrid. Now comes the tricky thing. How do we find out in which subgrid this number is contained. Okay, so let us also learn about this calculation that we are going to do. Okay, so for example, let's say I want to find out for this particular cell. So this is 0 1 2 3 4 5. This is 4 comma 1, and the subgrid for this cell starts at this particular cell. Okay, so if you look carefully, you can easily find out the subgrid. Let us say this is Sx and Sy, the starting point of subgrid, and this is x comma y. So Sx would be nothing but it would be x by 3 into 3. So let me show you. 4 by 3 is 1, into 3 it is going to be 3, and Sy is going to be 1 by 3 into 3, that is going to be 0. So this cell is actually 3 comma 0. Okay, and you can verify that this formula is going to work for every cell. Okay, so how this is going to work, I will just give you an idea. So you have a grid of size n, and it is divided into three parts. Okay, so we have three grids, n by 3, and same holds true for the horizontal and the vertical axis. Okay, so if I want to number these three squares from 0, I can give them numbers as 0, 1 and 2. Okay, so if I do n by 3, I get I get the grid number. Okay, so if this is 0 1 2 3 4 5 6 7 8. Okay, so if you just divide them by 3, 6 by 3 is 2, 7 by 3 is 2, 8 by 3 is 2. For them you get 2, for them you get 1, for them you get 0. Okay, and from this 2, you can see the starting point is at 6. So how do you get 6? You multiply it by 3. For this one, you see the starting point is 3. How do you get this? You multiply it by 3. You multiply this by 3. So this gives us the starting points. Okay, so let us try for this particular cell. This is 5 6 7. So this should be the starting point. So this is 7 comma 4. So let us find the starting point for 7 comma 4. So what we do, 7 by 4, 7 by 3 into 3, and 4 by 3 into 3. So 7 by 3 is 6, and 4 by 3 is 1, into 3 is 3. Okay, so you can see this point is actually 6 comma 3. So this formula really works. So once you know the starting point of the subgrid, you can iterate in a square of 3 by 3 from that starting point. Okay, so let us see this logic in the code. So what I'm going to do, I'm going to find out the square root, or I can simply do, I can assume that it's a 3 by 3 subgrid. So Sx is going to be I by 3 into 3. Okay, so let us assume that n is 9 in this case, and Sy is going to be j by 3 into 3, and for int x equals to Sx, x less than Sx plus 3, x plus plus, for int y equals Sy, y less than Sy plus 3, y plus plus. If matrix of xy contains this particular number, then we return false. Otherwise we return true, that this number is not present in the row, column, or in the subgrid. So this is our helper function, and we are done. Let us print the solution. For int I equals 0, I less than 9, I plus plus. For int j equals 0, j less than 9, j plus plus. See out matrix of ij. One thing I need to change, this is the recursive call that is actually solved Sudoku. Okay, so This is solve Sudoku, and we are good to go. So let's build our code and try to run it. So I want to solve Sudoku. So you can see this is the output I'm getting, and let us just verify for few random grids if we have all the numbers from 1 to 9. 1 2 3 4 5 6 7 8 and 9, which seems fine. Do we also have the numbers which are uh, so we should have 5 and 9, so we should not replace the original numbers. We have 5 and 9 here, and let us look at each row. So you look at this row, it contains all the numbers. You look at this row and this column, okay, or you look at this row, it contains all the numbers from 1 to 9. And maybe you also look at this subgrid, it contains all the numbers in the range 1 to 9, and this is true for all the subgrids, and that means our solution seems correct. Okay, so we got a correct solution. So I hope you really understood this logic, and you are now able to implement this Sudoku solver. And this is the backtracking step that you should not miss. And another mistake that people do is they forget to add the return statement. So this is very important, otherwise you will not able to propagate true or false that you are getting from the sub problem to the previous call, and you will get stuck. Okay, so these return statements are actually important here. Okay. So that's it for this particular problem. Thank you. I hope you learned a lot of new concepts.